talk more about radiation from point charges today. Some special cases. So this is pretty much where we left off before the recess, right? So we had the case where the point charge is at rest, so velocity is 0. First of all, we had identified what's part of the electric field from a point charge, when an accelerated point charge contributes to radiation. Right? That was the one with the extra length r here, so that it drops off only as 1 over r. Right? That's the only thing that contributes to radiation. And well, if we know the electric field from that contributes to radiation, we know the magnetic field is simply related by 1/c across. In one of the homework problems, actually, this would have been an easier way to calculate the magnetic field instead of just calculating the curl A. This would have been perfectly done as well. Good. So, well, remember the definition of this U vector there, unit vector RC minus V. And so if the charge is at rest, then the whole problem simplifies quite a lot. So if the P drops out everywhere, then we calculated that we have this characteristic sine square theta characteristic, just like for an accelerator, for a dipole, right? For an oscillating dipole. So if the acceleration goes, say, in the z direction, theta is the angle with respect to acceleration, then most of the radiation comes out here at 90 degrees. Nothing comes out actually in the direction of the acceleration. And we had calculated the total loss schedule radiation. But now, of course, this is just one very special case. Most of the time, we won't be able to do the calculation in a frame where the particle is instantaneously at rest. So the velocity will normally not be 0. So in the more general case, we'll really have to plug in here what the velocity is, calculate the cross products, and for the general case that can be quite messy, we'll just discuss a few special cases, 2 actually. But before we do that, there's one extra term that we have to take into account here, right? So, naively, you would simply then take your radiated electric field, not with the proper velocity, calculate what the Poynting vector, and then see what the radiation is that comes out. But there's one little trick with that. So let's say our charge is here and moves with some velocity in that direction. And assume we receive that radiation. So radiation, of course, moves out with velocity c. And we are sitting somewhere here far away, right? Now the rate, let's say at any point the charge radiates something, let's say that's wave crests, one after the next, that go forward. And of course move towards us as well. Say at some kind of interval, some delta t. But now, at what rate do we actually receive this? If, say, between one wave crest and the next, there's some time delta t, well, by the time this thing emits the next wave crest, it's actually moved a little bit. So we are, in fact, receiving the light from here. So the light actually has a little bit less distance towards us than from the previous wave crest. So what is the difference here? So what is the difference? It is this difference here that the light has to travel less from here than from here. So that means, what does that mean in terms of the frequency at which we see light or radiation coming out? It's a shorter time interval between them, so we actually see a higher rate of radiation coming towards us. Okay. So what is this delta L here? So let's make that a little bit larger. Let's make one interval. Let's say this is delta t. So the length that we're we're traveling here is velocity v times delta t. The difference that the light has to travel less from here is, if we are looking at some angle theta, so the difference that the distance that the light has to travel less is this distance here, right? That is v delta t times cosine theta, right? So that means the time difference at which we receive this is the real time difference minus, so the time that the light takes less here is this over speed of light, plus the radiation travels with speed of light. So it's minus e delta t cosine theta over c, right? So the time interval at which we receive it is the actual time interval with some correction factor, 1 minus beta cosine theta, where I've just defined beta as the speed over speed of time. So that means essentially the rate at which we receive radiation here is the rate at which that is emitted here divided by this factor 1 minus beta cosine theta. So that means, so we can write this 1 minus beta cosine theta, or this is 1 minus e cosine theta over c. Now that is v cosine theta, we can write as 1 minus, this is cosine theta, is now, this is our direction here, right? This direction. So this is 1 minus our unit vector dot v, right? Over c. The definition of this dot product here. And that we can write as CR unit vector of u over R dot u over R. Out R dot our unit vector, this is length R times C, cancel that out, it's 1. And the second R dot V, that can cancel out the length. Okay, so that means we can actually calculate the radiation from the moving point charge. Now really taking this correction factor into account. So if we calculate what's the power emitted per sort of solid angle is, which is essentially R squared times S absolute value essentially, right? So this, we calculate essentially this term, but with this correction factor R, so that's 1 over C R dot V over R C times squared direction. Okay, so now we just have one little correction factor here. It's essentially this time contract, this light travel time effect correction factor. That is the power emitted per solid angle, and then the total radiative power, of course. We will have to integrate that over all angles. So we can write that out. So that means, so this is 1 over mu naught C. Then see, this has, the square has 6 powers of R dot u, one of them cancels out. So maybe just write this out, r dot u over rc, and then we have the squared here is q squared over 16 y squared, oops, not squared, r squared over 6 power, right? And then cross. Right? Okay, now what cancels out here? So there's one here that cancels one of these. 5 here that cancels one of these. We have 2 c's here. And 1 over mu naught c squared is epsilon naught, right? So this just cancels out. So if I didn't miss anything up, did I? Okay, so now we have 5 lengths of r here, 3, 2, okay, so and we had to multiply in r squared here, so this actually gives us r cubed, and that's still a 4. Alright, so we have lengths of r, 3, 4, 5 lengths, here's 5 lengths of r. So we can replace everything just by argument vectors. So that means so the power per solid angle we can write as q squared over 16 y squared epsilon naught A squared over right. Okay, so that looks not too nice, but we'll breathe some life into that with 2 special cases that we can see what that actually means. So this is our radiative power per solid angle. Okay, and now, actually even the textbook doesn't really do this angle integration properly, and apparently, I must admit I've never done it myself either. If we actually integrate this whole thing over all solid angles, then we're well done with this. So, number beta was C. What would come in here is a factor called the Lorentz factor gamma. You've had some exposure to relativity, I guess, in the modern physics class, I think, right? So I think you have already some idea of what this means. If maybe either later today or latest next week, we'll actually motivate where this comes from and what the meaning is of this Lorentz factor. But the definition just being 1 over square root of minus beta squared, or 1 b over c squared. So with that, the total radiative output, so the total P radiative, so being P over omega integrated over all omega, we can write as mu naught q squared gamma to the 6th power over 6 c, and then a squared minus b plus a, isn't right? try to actually do the integration yourself, please feel free. It's quite lengthy, you wouldn't very much trying. So this is what you get if you just integrate this overall solid. Okay. Now let's see what that means for some special cases. The first case that actually the book discusses as well would be special case, so case A, let's call that, is where the velocity is in the same direction as the acceleration. Meaning it's simply linear acceleration or deceleration as well. Actually, the more relevant case is in fact if something is just essentially stopped. That gives radiation, right? It's an accelerated motion, it's a negative acceleration. So what we're calculating now is essentially what one calls braking radiation. So the radiation that is caused if the charge is moving fast and then is decelerated through something. Okay, so what do we get if V is perpendicular, is parallel to A? So first, let's see, R dot U is still going to be, so R unit vector dot U is still going to be R unit vector dot, R unit vector is 1, so this is C minus, and then R unit vector dot B, and this we can write as C1 minus beta cosine theta, right? Because C times beta is V is the velocity, and the cosine theta is the angle. So now we actually have the velocity going in the same direction, right? And cosine theta is just the angle between us and the velocity. Okay, then what is the U cross A here? So then U cross A equals, so we have, so this is R unit vector C minus V cross A equals, and the nice thing, if V and A are parallel to each other, then the V cross A term goes out. Two things are parallel to each other, the cross product is 0. So this then drops out, and it all comes down to just R unit vector C unit vector plus A, right? And that, so now R cross A, in what direction is that pointing? This cross this gives you something that comes out of the board. That is the phi unit vector, right? That's the phi direction. Because it wraps around. So this is, and how long is that vector? This unit vector here, there's C and A, and the angle comes in there. How? This, of course, C times A times something with the angle theta. How long is the vector, the cross product of two vectors intersecting with an angle theta? Sine theta, right? So that when theta is 0, sine theta is 0, the cross product is 0. And so sine theta, that goes in the phi direction. And then was R cross U cross A is just our unit vector across that. So we have the phi vector here, our unit vector across that, and does something in theta direction, right? So gives us C A sine theta in the theta direction. Alright, so we have everything here. That means the power per solid angle is q squared over 16 pi squared epsilon naught. Square of this is c squared a squared sine squared theta over this c. We have 5 powers of c here, c to the 5th, 1 minus theta cosine theta 5th power, right? Okay, c squared here, 3c squared, 3c epsilon naught c squared is mu naught, right? So get that out and put mu naught here, then we have our final result. Okay, so how does that look different now from this non-moving case? We have the same thing, of course, radiation propagates out in the radial direction as always. We still have the sine theta, so we still have this characteristic of nothing coming out in forward or backward direction. But what does this thing do now? So let's assume that beta is of course always, this is always less than 1. But let's say we're relativistic, we're moving with almost the speed of light. So beta is almost 1, just a little bit smaller than 1. Then you have 1 minus 1 cosine theta, right? So if cosine theta also gets close to 1, so cosine theta is 1 for 0 degrees for forward direction. Then we have 1 minus something that's almost 1 here. And 1 over that becomes very large, right? So that means this becomes very large when you go towards the forward direction. But if you're exactly forward, then you have 1 minus beta here, but the sine theta becomes 0. So you have still nothing in the forward direction, but a very small angle that's about 1 over the Lorentz factor. There you have most of the power coming out. And that goes in both directions. Almost nothing in the backward direction. Of course, also nothing exactly forward. But instead of having this sine theta, this tire essentially around here, z axis, this is all kind of boosted forward now. It's something that we'll discuss much more in the next 2 weeks or so. From relativistic motion, and all radiation from a relativistically moving particle that moves with almost the speed of light is strongly beamed and boosted in the forward direction. See that, right? And then we can do angular integrations. First of all, any questions here? Does this make sense? It's really just plugging in the special case where the acceleration goes in the direction of motion. Now we do the total angle integration. When you integrate over theta here, you don't need to carry that through, just do some substitutions here. The total P, so integrate over all solid angles. What we get is u naught q squared a squared over 6 pi c times 6 powers of the Lorentz factor. So again, it's almost the same as we have here, only that this funny beaming, this relativistic aberration, as we'll call it, so that everything comes out not just perpendicular to acceleration, but strongly beamed in the forward direction. That, so if beta is almost 1, that means gamma is actually a very large number, much larger than 1. So that means the radiative power is actually very strongly enhanced by 6 powers of this Lorentz factor. So this is 1. You can also look at, so if this is all correct, if it's supposed to make sense, then of course if we actually set the velocity to 0, then we should get back to what we have here. Right? Just quickly verify that we haven't messed everything up. So say if the velocity is 0, that means beta is 0, and what's the value of gamma when the velocity is 0? 1, exactly. Gamma equals 1, right? So if we set, maybe we can start here first. So the radiative power, if the velocity is 0, this term drops off, gamma is 1. We have mu naught q squared a squared over 6 pi c, gives us exactly what we need. So that makes sense. That's good news. So if we do that here, power per solid angle, the sine theta, everything is there, only that the beta is 0, so this term goes out. And that's precisely what we have here. Right? And the total radiative power, gamma is 1, then of course, that again just goes back to our normal form. So it all makes sense in the limit where the velocity is actually 0, we get our whole results. So, again, main points is that the radiation is strongly enhanced when particles are moving very fast and are accelerated, and all the radiation essentially comes out in almost the forward direction. Any questions on that? Does that all make sense? If it does, then we can go to another application, another special case, and one that's particularly important for astronomy as well. So we'll derive a result if you decide to actually go into astronomy, if you're considering doing a master's or PhD with me, when you derive one result that I expect all of my students to know if I wake them up at 4 o'clock in the morning, that's something you have to have present. So, synchrotron radiation. Does anybody know what synchrotron radiation means? This is synchrotron. It's actually a kind of particle accelerator, yes. So when you have a magnetic field, particles in a magnetic field spiral around, right? It's going in a circle is an accelerated motion, accelerated, so you have an acceleration there, you get radiation. So that's essentially what it is. So synchrotron radiation. So in fact, the main thing is that you have some magnetic field B in some direction, and you have a particle essentially spiraling around, moving with some angle, say alpha, between the velocity and the magnetic field, which means it will spiral around like that. Okay, then, in order to use those expressions there, what we'll actually do, so we know that all the radiation will still come out essentially in the direction of motion of the particle. What we will actually derive is just the final result for the total radiative power. So we can figure out what the total energy loss in radiation is due to synchrotron radiation. What is the acceleration on the particle here? That's the Lorentz force, right? The Lorentz force is, say we have some charge Q here. That's Q specific. Let's say we're dealing with an electron, so that's the elementary charge E. Then, what's the Lorentz force? What's the force of the particle moving with speed v at an angle alpha to the magnetic field? Lorentz force is, that's the first thing that everybody needs to remember. In what direction is it pointing to begin with? If you have velocity v and some magnetic field b, that's perpendicular to that, it's the cross product. Right? So there is just v cross b, right? And simply just the charge of that. Okay, and that something that we'll only derive, I think, in 2-3 weeks or so. Would naively assume that this is simply just m times the acceleration, but we'll see that relativistic effects actually lead to some extra factor, a Lorentz factor gamma here, as the relativistic force term. Effectively means that the effective mass is actually increased as you move at a very large speed. But we will derive all that in the next few weeks. Let's just take that as a given for now. So that means our acceleration is d v cross v over n, right? Okay, so what else do we need? So we need v cross a over c squared there. So we need v cross a equals, well, this is already perpendicular to v, so that's the absolute length. We're not interested in the direction for now because you see in the formula we only need the length, we also need the absolute value. So this is the length of this, just with one v multiplied, right? So this is v squared e over gamma n, and now of course from the cross product there's the angle alpha coming in, sine alpha, right? Sine alpha. So that means the term we need for the radiative power, that is the term a squared minus v cross a over c squared. That is, so this is, we have e squared, sine squared alpha over gamma squared m squared, right? That is just our a squared here, simply from there. And then minus, well, we have exactly the same, but let me just write that. We have this thing squared over c squared, so e squared v to the fourth, v squared sine squared alpha over gamma squared m squared c squared m, right? Right, yes. Let's just pull this thing out here. E squared, v squared, sine squared alpha over gamma squared m squared 1 minus. And what do we have extra here? We have v squared over c squared here, right? Now, if you remember the definition of the Lorentz factor there, that gives you, so 1 minus v squared over c squared gives you, this is a 1, that is a 1 over gamma squared, right? Okay, so now let's put this together. So the radiative power of synchrotron radiation. Let's just collect everything we have there. mu naught. Then we have the charge is E. This E squared there. This is going to be another E squared from here. So E to the